Use angle bisectors to find distance relationships. Incenter. The incenter of a angle bisector is the point of concurrency. So the point of concurrency of the three angle bisectors is called the incenter. So let's go ahead and draw a triangle, and let's bisect each of these angles. Now, when we were talking about the circumcenter, remember we started at midpoint. But for the incenter, I need to start at the angles and bisect each angle. And then I get the incenter of it. Right, theorem 5.5. If a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. If AD bisects angle BAC and DB is perpendicular to AB, and why perpendicular? Because perpendicular gives us the shortest distance. So that would be the closest point from D to that ray AB. Then DB equals DC. So we have the converse now. If I tell you that DB equals DC and they meet at right angles, then you can say that the angle itself is bisected by this ray AD. So you would say that these two angles are the same. Okay, example 1. Use the angle bisector theorem. Okay, do you see that EC and ED are the same? Do you see that they're also right angles? So we know now that this angle and this angle will be the same. So if this angle is 31, then the other angle, CBE, is also 31. Okay. Web. A spider's position on a web relative to the approaching fly and the opposite sides of the web forms congruent angles as shown. Will the spider have to move farther to reach a fly toward the right edge or the left edge? The congruent angles tells you the spider is on the bisector of LFR. So by the angle bisector theorem, the spider's equidistant from FL and FR. So the spider must move the same distance to reach each edge. Use algebra to solve a problem. For what value of x does P lie on the bisector? Well, we want P to be the same distance from P to K as from P to L. So we're just going to set the two segment lengths as equal. X plus 1 is 2x minus 5. Subtract x, and so we get x on this side, add 5, so x equals 6. Point P lies on the bisector of angle J when x is 6. Okay, concurrency. Now remember what concurrency means? Just 3 lines of a triangle meeting at the same point. We've already had the circumcenter. We've already had the incenter. So this is a point of concurrency when you have angle bisectors is equidistant from not the angles anymore, but from the sides of the triangles. So if AP, BP, and CP are angle bisectors, then PD is PE, which is also PF. So to draw this incenter, we need to start at the angles first and bisect each angle, bisect that angle, find the incenter, and then draw to each side as a 90-degree angle. That would mean that these 3 little lines are the same. Okay, in the diagram, L is the incenter of FHJ. Now, what does that mean? The incenter is the equal lengths to the side. So this little line, and this little line will be the same. Okay, now we need to find LK. So where is L? That's L up there. And where is K? K is right here. So I need to find this length right here, L to K. Okay, now notice that I have 2 numbers over here. And then we also know that this is right angle here. So I could just use the Pythagorean theorem to find this line. If I found this line, then I automatically have the other line because they're all equal. So we're going to say that 15 squared equals 12 squared plus x squared. And then, by the magic of algebra again, you're going to get down to 9. When you take square root, it's 81. It'll equal 81 equals x squared. And so 9 equals x. Now we know that if we're taking this true root in algebra, we would say either plus 9 or minus 9. But in geometry, distances can never be negative, so I'm just going to take the positive square root. So since x is 9, and that's one side of my incenter, the other side, LK, will also equal 9. Okay, go ahead and finish up the checkpoints at the bottom, and you're done.